Assalamualaikum and good day to all of you. So today I will continue chapter 4 magnetic circuit for part B. So last week I already discussed magnetic circuit part A. Okay, so these are the contents for part B. So this part B, it involves with magnetic circuit analysis, where you have a few arrangement of magnetic circuit. The first one is series magnetic circuit given phi, and then you have to find Ni. And then you have series parallel magnetic circuit, and then you have series magnetic circuit, but given Ni, you have to find the phi. And then properties of magnetic materials, magnetizing a specimen, hysteresis, demagnetizing process, and then magnetic field measurement. Okay, so what is Ampere's circuitous law? So Ampere shows that the algebraic sum of MMF around a closed loop in a magnetic circuit is 0. So this one is actually same like in electrical circuit analysis where you have KVI. So the application and then the step is the same with KVL. So last week we learned that F equal to Ni, and then you rearrange to get this one. So total of Ni equal to total of HL. Okay, and then this formula is depend on the type of material of your magnetic circuit. Okay, so for example, refer to this magnetic circuit. So you have to identify how many types of your material used in the magnetic circuit. So here you can see that you have laminated sheet steel, so one material. Okay, and then the second material is cast iron. Okay, so this is your cast iron. Start from here to this section. Okay, and then you have air gap. Okay, so air gap also you have to consider other material. So you have air gap, and then you have your source. Okay, so now you have 1, 2, 3 material involved, and then one source. Okay, so from this equation, so Ni equal to total of Ni, so Ni is at your sources, so N is number of turn, and I value of current supply, so equal to total of HL. So now you have 3 types of material, so you have, okay, Ni you only have one source, so this is your source. Okay, total of HL, so you have 3 material here. So that's why you have to identify how many material used in your magnetic circuit to check back and then to formulate the equation of this one. So you have Ni equal to HL of your iron, cast iron, plus HL of your sheet steel, plus HL of your air gap. So since it have this magnetic circuit has 3 materials, so you have 3 different HL. And first we look into analyze the series magnetic circuit given phi, and then you have to find Ni. So there are basic series magnetic circuit problem can be solved using 4 basic steps. So these are the steps that can guide you to solve the problem of magnetic circuit analysis. So first you have to draw the equivalent Ampere circuitous law model. And you have to calculate B of flux density for each section. So what it means each section is you have to calculate B B for each material involved. So depending on your magnetic circuit. So each material. Okay. So using B equal to phi over A is your area. So this formula we already learned in part A. And determine H for magnetic section from BH curve. So once you get the value of B, so you can refer to BH curve to get the value of H. So this one also we have learned in part A, how to read the graph. And then calculate Ni using Ampere circuital law. So this one using total of Ni equal to total of HL. Then use the calculated Ni to determine coil current or turns as required. So depending on the question, let's look into this example 1. Okay, if the core of the following figure in cast iron and the flux is 0.1 times 10 power minus 3 Weber, what is the coil current? So this one, you have to find the Ni given value of flux. So flux is phi equal to 0.1 with power of minus negative 3. Okay, so first you have to study the circuit and then figure out the material used for magnetic circuit. So this circuit only use cast iron for the material. Okay, so first step, you have to draw the Ampere circuital drawing. So you have one source, okay, here, and then source, this is how you draw the source, same as electrical circuit analysis. So this is your source, and then you want, so this one you only have one material, cast iron. Okay, so cast iron material, so we refer as a resistance. Okay, so since you only have cast iron, so you only have one resistance. So this one is for HL for cast iron. Okay, so if the magnetic circuit you have other material, for example cast iron section, and then you have other section for sheet steel. So for sheet steel you have to add one more resistor. Okay, so you have HL for sheet steel. So since this example only involve cast iron material, so you only have one resistor, HL for cast iron. So from the Ampere circuital law, so Ni equal to HL. So this one is Ni equal to HL so this one, let me erase first. Okay, Ni equal to HL cast iron. So you can write it H iron, L iron. Okay, and then given these are the information given in this question, you have mean path length, which is your L. So this is your L. L for cast iron, and then N is number of turn given, and then this question already give you the value of area. So this is your A. Okay, so first step, this is you have to draw the equivalent circuit of your magnetic circuit, and then the second one, you have to write the Ampere circuital law, formula. Okay, this one already given, BH curve. So as your reference to solve the question. Okay, so once you already draw the circuit and then the formula of Ampere's second law, next is you have to find the B. Okay, so next step you have to find the B. So this one refer to this. So draw the equivalent Ampere circuit and then you have to find flux density for each material using B equal to V over A. So you have to find B of cast iron. So B iron equal to, so V over A. So the information of V or your flux is given 0.1 times 10 power minus negative 3. And then your area of your magnetic circuit already given to 0.2 times 10 power minus 3. Okay, and then calculate, you will get 0.5 Tesla. Okay, so now you have the value of B. So next step you have to find H. Okay, so H iron. So this one, to get the H iron, you have to refer to the BH curve. Okay. Okay, so we refer to BH curve. You already have the value of B 0.5. So cast iron. So you have to identify which material. So from this example, we use cast iron. So you just refer to this curve. Okay, the value of B is 0.5, correct? Okay, 0.5. Okay, so we assume 0.5 here. Okay, 0.5. Okay, so you can use your calculator. So for example here, so this is around 1550. Okay, you can use your calculator to you can use your ruler to get the exact value from this graph. For example, this value is around 1550. Okay, so from BH curve you will get H iron equal to 1550 ampere turn per meter. Okay, so these are the information you already have, B and H. Okay, next step. Okay, this one you already done, and then calculate an I using Ampere second law. This is your Ampere second law. So N I equal to H iron L iron. Okay, so therefore I equal to H iron L iron over N. N is your number of turn. Okay, you already have all the information. So H is 1550 times L is already given. So L is 0.25 and then divide by number of turn given in the question. Okay, solve it, you will get Therefore, I equal to 0.78 ampere. Okay. So these are the simple example for series circuit to solve the magnetic circuit analysis. So you just need to follow the step. Okay. Okay, next is example 2, also series circuit. The following figure shows a portion of a solenoid. All parts are cast steel, and then your flux is 4 times 10 power of minus 4 Weber. When I is 2.5 ampere, find the number of turns. So this one also same analysis like the example before. So you have to find, okay, first of all you have to draw the ampere circuit equivalent ampere circuit. Okay, so first draw the equivalent circuit. Okay, so to draw the equivalent circuit, you have to identify how many material used in magnetic circuit. So you have, this is your plunger. Okay, so this is your yoke. Okay, so from this diagram, you notice that the cross section for each, for example, yoke is different between the cross section of your plunger. So you have to differentiate. Okay, so first you have to draw the source. This is your source here. Okay, and then you have one material is plunger, so you draw the resistor for plunger. So this is H plunger and plunger. Okay, next, okay, here you can see you have two air gap, okay, at this side and this side. So you have to draw two resistors for your HG. So H gap, air gap, L air gap. Since you have two, you have to draw two. Okay, and then the next material is your yoke. So you have to draw one more resistor for H, yoke, and yoke. Okay, so this is your complete equivalent circuit of your magnetic circuit. Okay, and then from this one, so you can formulate your ampere circuit law. Total of Ni equal to total of HL. So here you have only one source, Ni equal to, so HPLP plus, so Hg for air gap, so you have two air gap, Lg plus HGLG plus H yoke L yoke. Or also you can write it as Ni equal to H plunger L plunger plus 2 HGLG. So you have two air gap, 2 HGLG plus H yoke L yoke. So these are the ampere circuit formula. Okay, next you have to find flux density for each material section. So okay, so sorry, this is second. So find V for each section. So you have section for York. Okay, how to find? So let me copy. Okay, let me copy this. And okay, for York. Okay, so for cross section, for York is 2.5 times 2.5 cm. So remember, B equal to flux over A. Okay. Okay, flux already given. So you have to find area of York. So area of York is area of York is 2.5 cm. 2.5 cm times 2.5 cm. Okay, this one you have to convert to SI unit, meter, so you will get 6.25 times 10 power of minus 4 m square. Okay, so once you get the area, so you can find the B. So B York equal to, flux given is 4 times 10 minus 4 over 6.25 power minus 4. So value of B is, so use your calculator, you will get 0.64 Tesla. Okay, once you get B for York, you can get the value of H. So refer to BH curve. Okay, so 0.64 BH curve 0.64. So okay, 0. We use casting 0.64 here, 0.64, 0.64 here. Okay, you can use your ruler. Okay, your H is around 410. Okay, maybe 400 or 410. Okay, so this one, your H, G, HY, H York. Sorry, this is your H York. Equal to around 410 ampere turn over M. Okay, and then you repeat the same step as York. You have to find next plunger. Okay, so for plunger, you have, since the cross section between plunger and York is different, so you have to find area for plunger. Okay, area for plunger. A plunger equal to 2.5 cm times 2 cm. So 2.5 cm times 2.0 cm, you will get 5.0 times 10 power minus 4 meter square. Okay, apply the same process. B P equal to flux over A. So 4 times minus 4 over your A for plunger is 5.0 times 10 minus 4. So B plunger you will get 0.8 Tesla. Okay, refer to your BH curve. So H plunger 0.8. Okay, 0.8 here for cast steel. Okay, around 500. Okay, your H is around 500. So H for plunger is around 500 ampere turn over M. Okay, next you already solved for yoke and plunger. The last is for air gap. Let me add the slide. Okay, you have to find gap. Okay, air gap. Okay, there are two identical gaps, so you have two air gap. So we assume that B flux density at air gap is equal B at yoke. Why it happened is, you can see this is your air gap. Okay, you have two air gap, 1 and 2 here. So you can imagine your gap is here. Okay. Okay, so your air gap is here. So we neglect the fringing effect. So you can see that the cross-sectional of your air gap is actually same with the cross-sectional of yoke. So that's why by neglect the fringing effect, we say that B at air gap is equal to B at yoke. So therefore it will be B yoke is 0.64 Tesla. Okay, to get the Hg, you have to use the formula of, so remember before this we have learned B equal to mu H. Okay, since it happened at air, so B equal to mu naught. Naught is happen at air, mu naught Hg. So to get the Hg, okay, air gap, you cannot refer to the BH curve because the BH curve is only for cast steel, cast iron and sheet steel. Okay, to get the value of Hg, you have to use this formula. So Hg equal to Bg over mu naught. So value of mu naught is constant. So Bg 0.64 over, so mu naught Okay, so the value of mu naught 4 pi times 10 minus 7. Okay, use your calculator, you will get 5.09 times 10 power 5 ampere turn over amp. Okay, so you already complete finding B and H for each material. So next step, you have to, from the Ampere law formula, where Ni equal to HPLP plus 2, you have to get, okay, plus H yaw L yaw. Okay, so the question asks you to find N. So N equal to HPLP plus 2HGLG plus H yaw L yaw over I given. So you just substitute all the value we already get from the previous step. Okay, and then divide by I, you will get 4204. I is 2.5, so equal to 168210. Okay, so these are the process you need to follow, or the step you need to follow to analyze the magnetic circuit in series coordination. And then for series parallel magnetic circuit, so before this we do the analysis for series magnetic circuit. Now we look into analyze the circuit for series parallel magnetic circuit. So you can see that you have section, and then with the series and parallel coordination. So this one, the core is cast steel. Determine the current to establish an air gap flux. Flux air gap equal to 6 times 10 power minus 3 by neglect the fringing effect. So these are the information given. Okay, so this one I only discuss the step. Okay, so at the air gap section, you have BG equal to flux G over A. So flux of G already given 6 times 10 minus 3. Okay, divide by area of your air gap. So you will get 0.3 Tesla. So, and then you have to apply, for air gap, you have to apply this formula, Bg mu naught G Hg. So to get the G, to get Hg equal to Bg over mu naught. So you will get this from this value, Hg equal to 2.388 times 10 power of 5. And then section AB and CD. So AB equal to, let me copy the, see. Okay. So BAB. Okay, this one, this section, AB is equal to section at CD, okay? Okay, and then air gap happen here. So this is your air gap. So that's why I say that you can say that flux density at AB equal to flux density at CD. So this is your air gap, so equal to 0.3 Tesla. And then, so once you get B at AB equal to B at CD, 0.3, so refer to the BH curve of your BH curve. You will get BH curve of Castile. You will get with BG 0.3, you will get HAB equal to HCD equal to 2.250 ampere turn over meter. So this one is from BH curve. Okay, this one, since it is parallel, so you have to draw loop 1 and loop 2. So same application, KCL or mesh analysis. So value of sum of Ni equal to sum of HL. So since you are going opposite to the flux in leg DA, so DA, okay, the corresponding HL will be subtractive. Also Ni equal to 0 for loop 2. Why Ni equal to 0 at loop 2? Because you don't have source here. The source only at loop 1. So 0 equal to total of HL at loop 2. So 0 equal to HAB LAB, okay, here, plus your HG air gap, L air gap, plus HCD LCD. So minus because the direction is opposite, that's why you minus here, because this is opposite with phi 2. So HDA LDA. Okay, so HAB 250 times 0.25 is the length of AB given, plus HGLG, so HG 2.388 times LG also given, okay, and then plus HCD 250 times LCD given 0.25 minus 0.2 given L of DA given times HDA. Okay, so you rearrange and then solve the equation. So thus 0.2 HDA equal to 184.7. Okay, so from this one, so HDA equal to 925 ampere turn over meter. So and then you already have the value of H. So this one is opposite. Before this you have from B you can find H from BH curve. But now you have the value of H, so you can find the value of B. So with the value of H is 925. So refer to BH curve, you will get BDA equal to 1.12 Tesla. So this one is from your BH curve. Okay, so this one is like mesh analysis. Okay, So flux equal to flux 2 here. Okay, so you have BdA. So flux 2 equal to BdA times A. So you will get 2.24. And then for flux 1, so if you apply KCL here, so flux 1 equal to flux 2 plus flux 3. So flux 1 equal to flux 2 plus flux 3. So you will get 2.84. So BDEA is equal to, okay, let's copy this one. Okay, so flux 1 equal to flux 2 plus flux 3. So same with I in equal to I out. So flux 1 equal to flux 2 plus flux 3. And then BDA, BDEA. Okay, you want to get this values of this section. So flux 1, so because it involved with flux 1 at this section over A, so you will get 1.42 Tesla. And then HDA, okay, this one is once you get the value of B, you can find H, refer to BH curve. Okay, you get 2125. Okay, and then you apply Ampere law at loop 1. So loop 1 only. So Ni, you have source here. Sorry, you have source here. Equal to HDEA LDEA plus HAD LAD. So this is at this section only. Okay, so this section. Okay, HDEA plus HAD LAD. So you will get Ni equal to 929 ampere turn. So okay, how to get I equal to Ni, okay, so over your number of turns. So this one, Ni equal to HDEA LDEA plus HAD LAD. So I equal to, so 9 to 9 over number of turn over n number of turn 200. So you get 4.65 ampere. So the analysis of series parallel is quite complicated, but once you know the step of analysis, follow the step of analysis, you can solve the problem. Okay, and then series magnetic circuit given Ni, find phi. Okay, so before this you have to find Ni given phi, but this one is given Ni, you have to find phi. Okay, this one is actually you need to try and error. You have to use try and error method. Okay, so for example, this following given n equal to 25 turn, and then the current is 10 ampere. So this is your magnetic circuit. Okay, the solution for this one is so HL equal to Ni since you only have one material. So H equal to Ni over L. So N is 5. So this is actually 250, okay? So 250 turn over, sorry, 225 times 10, you get 250 over, your length is 0.2 meter. So we'll get 1250 ampere turn. So from the BH curve, so this is opposite from this one. So now you already have the H. So from BH curve, okay, your H is 1, 2, so 1, 2, 1, 2, 5, 0. So 1, 2, 5, 0 around here, and then your material is cast steel. Okay, cast steel is here. You will get around 1.24. Okay, 1.24 something. 1.24, let's say it is 1.24. So B is 1.24 from the H curve. Therefore, flux equal to BE. So 1.24 times your area is 0.01. You will get your flux is 1.24 times 10 power minus negative 2 Weber. Okay, so in the next example, if given your material is cast steel and I equal to 1100 ampere turn, the cross sectional area, whereas your A equal to 0.0025 and then your length is 0.002. Okay, and then the L steel is equal to 0.2 meter. Determine the flux in the core. So this one is actually try and error method. Okay, so these are the steps. Okay, so please study the step, and finally you will get the answer for flux is equal to 1.55 times 10 power minus 3 Weber. So normally the try and error method will not ask in your final exam. So this is for your additional information to solve the circuit analysis. Okay, and then next subtopic is properties of magnetic material. So start from this subtopic. It involves on theoretical information. Okay, magnetic properties are related to atomic structure. So each atom of substance, for example, produce a tiny atomic level magnetic field because its moving electron constitute an atomic level current and current create magnetic field. Okay, so for non-magnetic material, these fields are randomly oriented and cancelled. However, for ferromagnetic material, the field in a small region called domain do not cancel. So this is the field inside the ferromagnetic material. So where you can see the arrow is scattered at many directions. So it called domain do not cancel. Okay, if the domain field in the ferromagnetic material line up, the material is magnetized. So for example, you supply at the initial point, this is your field, and then when you supply the current, okay, and then the material will magnetize. Okay, the material is okay. So this, when you supply the current, the arrow of your direction will be at one direction only. Magnetizing a specimen. Okay, this is what I already explained before. So at the beginning, okay, your direction of the arrow in the atomic level is scattered direction. Okay, once you apply the current, so you can see that the arrow will be moved into one direction. Okay, so as the current through the coil is increased, the field strength increase and the more domain align themselves in one direction. Okay, when you add more current for your ferromagnetic material, so all your direction of your field will be in one direction until saturation point. So this is how you magnetize the ferromagnetic material. Okay, this is the explanation I already discussed. Okay, so when the saturation point, it means that once the material is in saturation, you cannot magnetize it much further, no matter how hard you try. So it will remain the same. Okay, past zero, a trace from the non-magnetizing state to the saturated state is termed the DC curve of normal magnetization curve. So this curve is actually normal magnetization curve. Okay, so and then what is hysteresis? So hysteresis is the phenomenon which take place when there is a magnetization and demagnetization of material. So H can be readily increased or decreased by varying the current through the coil of the wire, and it can be reversed and reversing the voltage polarity across the coil. So the explanation of hysteresis phenomenon, I will upload the video step by step how the hysteresis curve is plotted. So these are the detailed explanation on hysteresis curve. So please watch the video of the hysteresis phenomenon in ULEN. These are the explanation. And then the next is demagnetizing process. So this one also I will upload the video of demagnetizing process. So these are the steps. Okay, and then how we measure the magnetic field. So one way to measure magnetic field strength is to use Hall effect. This one if you want to apply at your lab work. So this is the diagram how to measure the magnetic field strength. So instrument used to measure magnetic field are known as Hall effect gauge meter. So to measure a magnetic field with such a meter, this is the probe connection, how we want to measure the field, magnetic field. So the meter indicates flux density directly. So if you got 473, so that is the flux density of your magnetic circuit. So that's all for chapter 4 magnetic circuit. So any problem on this syllabus or this analysis of magnetic circuit, so you can discuss in WhatsApp group. So that's all from me. Thank you.